All right, line V1, we are on to learning task number 5, where we are going to be looking at across the line starting. This is actually going to be video 5b, because we have already gone through the first part of, the 2-wire versus 3-wire control. We left off right over here at our 3-wire control circuits, where we had gone through the way that the coil and the sealing contact would work together to go and provide us with a path that can go and stay sealed in so that I can walk away from my start push button. And that is also going to go and provide me with that low voltage protection, which is going to be so critical to us. We're now going to start talking about add-ons. If you compare this circuit to the last circuit over here, what you'll note about it is that this circuit has just got an extra indicator light. That's all. All that I'm doing inside of here is I'm adding in an additional load onto this circuit. This is going to be a light that is going to go and tell me anytime that I've got power all the way through. We can verify that by once again tracking down all of our power through the circuit. So if I want, I can go through up to there. I can go through up to there. I see they've got line 1 and line 2, which I'm taking off of my main power circuit, right? These ones over here. And I'm able to carry them that far into the circuit, but we don't have any operation. I press my start. When I press my start, that is going to go and provide power all the way through up to there, which will energize this coil. When I do that, that is going to close that set of contacts, which will provide power back up to that coil again, and at the same time provide power to that indicator light. I can take my finger back off the button. We see that we're going to be sealed in, and that I'm going to go and have my indicator light glowing, as well as I'm going to go and have my contactor that's going to be in there. I can add in a ton of additional lights onto this thing. Basically, anything that I want to have active at the same time as my actual motor itself, we do that by placing those in parallel with this. We refer to this as rungs that we have over here, because I might have other additional things. Let's say I've got a horn that I want to go and add into here. I would go and add that in like that, and we would say that this is going to be added onto another rung onto here, because it looks like, the more devices that we go and place into here, the more rungs that we are going to go and have. Note that my loads must be in parallel. The wrong way to do this, and the way that I see apprentices do it all the time at the beginning, not that you're going to do it all the time, but you'll get smarter and you'll get better and move away from it. But the way that I see it at the beginning is this. Let me just white that one out. And I find a lot of apprentices that will go and try to connect that thing in series like that. If they connect it in series, yeah, they're going to be able to go and provide a little bit of power to it, but now we've got 2 series loads. What happens when I've got 2 resistances in series and I place voltage across them? They split the value of voltage, right? Whatever my VT was, each of them is going to go and get half and half. So my coil is only going to be operating at half voltage, and my light's only going to be operating at half voltage. There's a very good chance that that contactor itself is not going to be able to pull in at half values of voltage. Don't do it like that, okay? You should never have series outputs. Is this an output? Yes, it outputs light. Is this an output? Yes, it outputs magnetism. Never series your outputs. You must parallel your outputs. Let's take a look at what that looks like. That's these over here. Now we see that we can go and get full value of voltage across each of these over here. Adding in additional components is done by adding in starts and stops in parallel or in series, depending upon, what the component itself is going to be. Once again, note that this is going to be my base circuit right there. Draw that again. I was hiccuping as I was drawing, and it wasn't working. Actually, we're still missing that because that coil is all the way down there at the very bottom, or the sealing contact. But yeah, you get what I'm saying. You see that there's a start in parallel with my auxiliary contacts, which is then going to go and control my coil, and that is also going to go and have my stop in series with that. If we go and carry current through, we see that all of these are going to be blocking because they're going to be normally open. This is going to be up to there. We've got no operation. Which start button could I use to go and bring power to that motor? Stop for a second. Take a look at it. Tell me, which start could I use to go and bring power to the motor? You're smart. You just said all the start buttons could be used. Pick one, anyone. We'll pick number 2. If I take 2, it is then going to be able to go and provide power to that coil. The coil is going to go and energize, and the coil will then go and seal itself in, which would allow me to go and carry power through that one up there as well, and I can take my finger off of that start push button. You should see that any one of my start push buttons, provided that they are in parallel, will allow me to start my contactor over here and then seal this thing in. Let's take a look at the stops next. Which one of these stops is going to be able to stop it? Which one can interrupt current? Well, you're going to look at that, and in about 3 seconds flat, you're going to say, Joel, I'm no idiot. Those are in series. Any one of them would be able to go and shut that thing down. So we can pick any one of them. We'll pick number 3 this time. We'll open up number 3. When we open up number 3, it's going to go and interrupt all of my current. When it interrupts current, it is going to depower that coil. This contact falls back open. I take my fingers back off of it again, and at that point, I would be back down to my ready to start position off of here. You can add in an unlimited amount of starts and stops. Well, I shouldn't say unlimited. You do have voltage drop on the wire, but basically an unlimited amount of starts and stops just by seriesing the stops and by paralleling the starts. Okay? That's all that we need to do to go and add these things in. We do also have other times where we will go and provide manual or automatic, or sometimes what we refer to as jogging circuits that we're going to have. If you take a look at this one over here, you'll note that this one is really just a redoing of that first circuit that we took a look at, right? If you look at this one over here, they show, I'm just going to grab a marker here, that we've got the coil, and that we are just going to go and use a 2-wire control device to go and control that coil. I'm going to white that one out. We don't really need to go and have that one drawn in the way that they had it there. It was just kind of hanging down as a unused steam. That's a 2-wire control circuit. If I take a look at this, this is going to be a selectable 2-wire control circuit over here, right? If you take a look at this, if I move this selector switch up into that position over there, we would go and have power applied to that side. We would also see power applied across to this side, and we would see that this thing would be energized. If power would fail, or if an overload were to go and kick, we'll just kick this overload out over here. Oh, that's the wrong marker. If this overload were to go and open up like that, it is going to go and shut down our coil. But the second that I go and reclose this, that would go and once again repower this thing up. It is what we refer to as a 2-wire circuit. It provides a low voltage release. You'll note that it does not utilize the seal and contact. The seal and contact is the number one thing that tells you when you have got yourself an actual 3-wire protection type of circuit. This one over here is going to go and have release. If I go and break it from there, move it back down to there, we see that that would take out my coils. That's from the hand position. I move to the center position, which is going to be my off position. Some switches, there's not even going to be an actual contact screw. It's just going to have like a blank position inside there. And then I can move from there down to auto. And if I move this thing down to auto, you should recognize this thing as being a series circuit. So I can once again carry through up to my control device that is going to be stopping. In this case, it's going to be a float switch. The second that I go and provide water inside of here, and it's going to go and float that switch up, the switch is going to go and connect across here. When that switch connects across there, we provide power through into there. Going to start up the motor, whatever the motor is going to go and be. Maybe it's a pump or something like that. If it was a pump, it would start pumping this water down, and when it gets low enough, it would go and reopen this, shutting that thing off over there. Once again, if I were to go and have this contact held closed, let's go and put water into our sump over there. I'm going to put that in there. Put power going through up to there. We're going to have an energized coil at that point, which would mean that all of my contacts would be closed. The motor itself would be running. If I am running my motor like this and I end up with a power failure, that power failure is going to go and take out all power that's inside of here. So it's going to take that out, that out, that out, that out, etc. But it does not change my position of my switches, nor does it get rid of the water somehow magically, right? Probably we're getting more water in there. We're not pumping it out anymore at this point. Which means that when power does come back on, instantly the circuit is going to go and be released to start operation once again. This one over here is a two-wire circuit. Yes, it contains more than two wires, but we refer to this as a two-wire control circuit because the piloting device, that's what we call these, the piloting device is only got two wires coming off of it. Okay, we'll examine all of that a little bit more later on. The way to determine them, though, primarily is look for this. If you do not see a seal in contact, here's a seal in contact. Oops, that's not my highlighter there. There's a seal in contact on that one. This one over here has a seal in contact as well. If you do not see the seal in contact, you must be looking at a two-wire type. Talk about using overload relays with just a single overload device. What we've seen inside of here before was we had three individual overload units. Put that one back over there and erase this. These are going to be the actual overload heaters that we will have inside of there. And each one of them was going to go and have its own normally closed set of contacts. That's why when we saw all those drawings, just drawing that over there, why on every single one of those drawings we had three of these so that we would be able to go and trip out whether it's any one of these lines that's drawing too much current. It would be able to sense that, trip that thing out. In practicality, in most of our modern circuits, particularly when we're dealing with the IEC standard, we are only going to have a single set of contacts. Remember those little contactors that we showed the drawings of, the IEC standard style? There was only one terminal set that was labeled as being 9596, my normally closed set of contacts. That was sensing, it was reading all three of my lines going out to the motor, and then it was going to go and have only a single control component inside of here. Looking at this one over here, we see that we've now got kind of a holistic view of the entire thing, where we see the power circuit. That's going to be everything that is up top over here. All of that's my power circuit. Interfaced with my control circuit. That's going to be everything that's going to be down over here. And this thing does bring up an interesting little fact. What it talks about over here is this. The overload relay contact may be ahead of the stop button. Historically speaking, I mean, talking to the oldest electrician that you know, they will always want to go and place their overload relays down here at this end, because that was just the way that things always were done. But there were some problems that were developed off of that in certain types of circuits, particularly types of circuits where we had a ground that was going to be inside of it. This one that we see up top over here, yeah, we see that this thing does not have a grounded circuit. It's all three lines. It's a three-phase circuit. But if my control circuit was grounded, then there could be ways that we could bypass this with a fault. So we had, some special case scenarios where faults would go and prevent this from going and operating. The Canadian Electrical Code stepped in. When was this one? I think this was the 08 that we saw the change off of this one. Don't quote me on it. Doesn't matter. It's history anyways. But the Canadian Electrical Code stepped in, and under Rule 28506, it talked about a grounded control circuit. And it says, where power for a control circuit for a motor controller is obtained conductively from a grounded system. In other words, where I have got a grounded control circuit. The control circuit shall be arranged so that an accidental ground of the wiring from the controller to any remote or signaling device. So any accidental grounds onto any devices will not start the motor or prevent the stopping of the motor by the normal operation of any control or safety device in the control circuit. That's what we need to go and take a look at next. We're going to do that on the next drawing because the next drawing is completely screwed up because it doesn't follow through on this one. That's all right. That's why you got me. That's what I'm supposed to do is, guide you through whenever there's scripts. That's just historical stuff that has been around for a long time. I want to go and take a look at what we have happening over here. This power circuit over here is a 600 volt motor power circuit. And you can see that they're taking that 600 volts off and they're taking it to the primary of a transformer. Would you look at that? We've got an H1, H2. We've seen these things before. We've got a little bit of control circuit fuse protection inside of here as well. These will obviously be smaller fuses, only a couple of amps each, that are going to be protecting this whole system over here. The reason we're doing this is because this is a 600 volt line over here, and if I've got push buttons, my operators are going to go and, hammer on those things. They poke them with broomsticks, they hit them with hammers, they smack them. if you've worked around industrial applications at all, you will come across broken push buttons. The last thing that we want to do is have a 600 volt circuit in there where somebody is going to just jam their finger into what used to be a push button and take 600 volts across the fingertip. It goes very, very poorly. That's what would happen in this circuit over here. If this were to be a 600 volts, and if this were to be a broken push button and somebody were to just go and jam their finger into there, that's kind of a finger like that, that's going to go and obviously result in, arc contact across there. We don't want to go and see that, so we go and bring down to what we refer to as safer control values of voltage. One of our most commonly used control voltages is going to be 120 volts. We love 120 volts. We can get pretty much any device we desire in 120 volts. But because it is 120 volts, we also have to go and follow through the rules that are given to us inside of section number 10, grounding and bonding. I'm just going to roll up there really quick there. We've talked about this a number of times, but anytime that we have got a circuit that is going to be an AC circuit, what I need to do, let's just go up here, there we are. AC systems exceeding extra low voltage. We've gone over this rule like 20 times this year already, but exceeding extra low voltage, so above 30 volts, shall be solidly grounded if, by doing so, their maximum voltage to ground does not exceed 150 volts. You remember that whole concept of having the balloon that we use? We tie the balloon off, and that's going to go and choose how far above, Earth it's going to float. That's what we're looking at over here. Is it over 30 volts? You bet. So it has to be solidly grounded, particularly if it's not going to exceed 150 volts. Also always has to be if it's got a neutral, but this one here didn't have a neutral, it just had 120 volts. Going back to this one over here, we see that whoever put this one together did so partially properly up to a point. They took their two lines over here when they were starting to build this, and I'm just going to draw this thing. We'll remove all of this. We'll bring that all back in a second. And the very first thing that they did is they took one side of the transformer, they grounded down that side of the transformer over there, and then they applied a fuse into the other side of the transformer. This is 100% correct. Does not matter which side of the transformer they pick. Any electrical circuit can be grounded in one spot. If they would have grounded X1, then they would have had to put the fuse into X2. It's AC, it won't make much of a difference. This grounding over here means that if there were to be any sort of a fault anywhere along here, let's say that this thing were to fault to ground, then what we would get is we would get that massive amount of current, right, where we are going to have current that would then travel through the ground, back up through here, back through the transformer, and back to the fuse. It would kick out our fuse system. It's a protectively grounded system over here. What they then did is they connected in their starts and their stops. Now, the rest of the starts and the stops that they have inside of here, this makes sense. We take our line. If we have got a line and a neutral, then neutral is always going to go to my load side. Are we supposed to be switching a neutral? No. These are other rules in the code that we've talked about before. You never switch the neutral. You always switch the hot line. So in this case, once we've got one grounded conductor or identified conductor, we now have to go and switch the hot line, right? That's my hot line over there. So we switch the hot line. We see that all my switching devices are in. I've got my power now that we're going to go and carry through up to there and up to there. And we'll take our power through on the other side over here as well, up to there. Standard 3-wire control circuit that we have over here. Let's step through our operation, and then we're going to fault it. I close that. When I close that, current is able to go and flow through. This is going to energize. That's going to go and close my sealing contact. And when the sealing contact closes, it's going to go and, once again, provide power to that coil. I can take my finger off of this push button. At this point, what I have is I have got an operational circuit. If someone were to press the stop push button over there, obviously that's going to go and interrupt the current, and then we would lose the sealing contact and it would shut down. Or if the overload were to go and kick at this point, it would also go and shut down the motor, right? The overload, which is attached through heat to those, the contactor, which is attached magnetically to those. All of this is standard. Where we run into an issue would be if I had an unintentional ground. Going back into our code book over here, we'll roll back into that section 28. 28506 is where we want to go. Let's take a second to roll there again. 28506 says that the control circuit shall be arranged so that an accidental ground will not prevent the stopping of the motor. by normal operation of any safety device. Okay, we're just skipping some words and getting to the heart of it. So a ground cannot stop this thing, or cannot prevent this thing from stopping. Going back into here, if we were to have another accidental ground right over here between the coil and the actual overload relay itself, if this were to go and happen, we would have a parallel path going through, up through that ground and back out over here. Which would mean that if my overload were to go and trip out, open up, boom, like that, what do we see? We see that we've still maintained current through to that contactor. Having the overload over there, downstream on the neutral side, is illegal. You have to understand that. It is not allowed here in Canada. In British Columbia, we use the Canadian Electrical Code. Cannot do it, don't be the person that did it. If we want to stick an overload in, there's only one correct place to stick that overload in. And that would be upstream over here. We're just going to erase a whole pile of this. I'm going to draw in the overload upstream. We're going to go and examine this circuit one more time just to go and figure out how this thing would operate properly. I'm going to place it up here. Some of you are going to do this in the field properly. You're going to have a 120 volt circuit. You're going to try and run your line through the overload, and whoever you have that's supervising you is going to get pissy about it. Don't listen to them. Bring up 28506. Explain to them this whole thing on that overload. They need to be doing it properly. It's just going to take a long time to go and retrain all of the old electricians in our trade. It's not impossible, but it starts with you in some of these cases. And you're not going to be able to win that argument unless you've actually paid attention in this either. So, pay attention, make sure you know your code, and then you will actually be able to, make that effective change. Okay, we'll provide the power through my overload and my stop at this point. We'll take it up to there. We will go and take this circuit all the way down into there. And that overload relay, actually, I'm just going to erase that one. I'll stick a line all the way across it. Like that. I don't know, it might glitch out on me and hide behind it. Sometimes it likes to do that. But that's where we've got power all the way up to. Perfect. If at this point someone were to go and press the start button, do that right over there, that is going to go and provide power across to the coil, which is then going to go and energize, which is then going to go and close in its sealant contact, which is then going to go and maintain that power there so I can remove my finger from that button over there. We see our highlighted current flow happening inside of here. At this point, if I were to go and have that same ground that we had before. Remember how we had an improper accidental ground over there? If I were to go and have that ground over there, don't worry about the white blob, it's just the thing being janky here. But we see that this is not going to be able to bypass anything, because if my overload goes out over here, even with this ground in the system, the overload opens, and when it does so, it interrupts all current all the way through up to there, which means that this whole system is going to go and shut down. So this drawing over here, I want you to go and X that out. Fail. You can write that right next to there. You should also be writing these numbers, 28-506 over here. And then highlighting that to that 120 volts and that ground. Well, maybe don't draw all the circles there, but 28-506, because of that ground that we have inside of there, fail over there. That overload relay, I want you to go and draw it in at the beginning of your control circuit. That is the only proper place to put a overload in a 120 volt circuit, because a 120 volt circuit is going to be grounded down. Anytime that it's not 120 volts, it doesn't matter. Over here, they've got a three-phase circuit. Now, if this one were 208 volt, let's say, or 480, 600, whatever it would be, it wouldn't make any difference whatsoever, because either one of these is still going to go and cause an issue. If I get a trip or I get an accidental ground over here, that accidental ground is going to go and cause fault current to go and flow from here. Sorry, I'm going to do a different line there. It's going to be this one. It's going to be faulting off of line 2. It is going to go and travel through here at that point, and then it's going to go and follow back up all the way to my main power transformer. Once it gets to that main power transformer, then it is going to go and trip out. And it should probably have taken out that fuse that we have on that line as well. Note that this one is using line to line over here. That's why we're allowed to place the overload on this end. And because it's using line to line, we see that we have got fuses on both of these lines. This one over here has got 120 volts, so we have only one fuse, the other side is grounded, and then we have to move the overload relay. Okay, don't freak out about it if it's on a line-to-line one. That's completely fine. It's only on these grounded types that we have to worry about that. So this one is perfectly fine because it's line-to-line. Same with this one over here. You note that's line 1, line 2, so it's fine for the overloads to be at the back end. This one, line 2, line 1, both of those are lines, so we can have the overloads at the front or the back end, doesn't matter. This one too, line 1, line 2, overloads are correct. This one as well, line 1, line 2, overloads are correct. This one as well, line 1, line 2, overloads are correct inside of them. Okay, don't worry about the rest of them. It was just this bottom one because it was 120 volts. The first thing that you should do though, when you are looking at a control circuit diagram, is always identify the system. If you see one of these that is designated with a big old N, neutral, over there, you must not do that at that point. Then you just have to move them to the other side. It's not like you get rid of them, you just move them, so that's going to be done proper. Okay, that is it for self-test, or for learning task number 5. On to the self-test.